In this video, we're going to introduce for the first time a very fundamental concept in chemistry, which is called equilibrium or dynamic equilibrium. Specifically, in the case of phase change, let's remember that when we are trying to plot temperature versus heat, you start with solid, and then solid becomes liquid, and then you have pure liquid, and then liquid becomes vapor, and then you have gas. Okay, this is what the heating curve is, uh, and here you have solid and liquid and gas. What we want to talk about now is that what is really going on during this liquid phase, and if there are any molecules of gas at all. The answer is that yes, there is a certain equilibrium between liquid and gas, even when you have pure liquid. In this case, and that's what we call vapor pressure. Vapor pressure will be that fraction of molecules that, while still being most of your substance in liquid, already exist in gas phase. Or if you will, you can also call it smell. That's what a smell is. The smell is what your nose detects as the vapor pressure, the vaporized part of that substance that you are smelling. Okay, so to do that, we have a small simulation that I would like to show you. In here you can see what a very tiny ice cube of ice looks like, and so it's a solid. So notice what happens as we warm it up. Notice up here that you have almost 200 Kelvin. 200 Kelvin, this is still below zero, so expect to have ice. And notice that as we now the ice melts at 273 Kelvin, so now you already have liquid. But what happens if you warm it up a little bit more? Your water will not boil until 373, and yet even before reaching 373 you have some molecules existing in vapor form. Most of your molecules are in liquid. However, there are some molecules that are completely detached from the rest, therefore they exist as vapor. Notice that they also come out and come back. This exists as a dynamic equilibrium. It's never the same molecule existing as gas or existing as liquid. So that's what we call a dynamic equilibrium. There will be always a dynamic equilibrium between the liquid and the gas, and that equilibrium will reach a point where molecules leaving the liquid getting into the gas is the same number of molecules of going from gas to the liquid, and that's what you see here when the rate of vaporization is equal to the rate of condensation. Even in pure liquid, we are not boiling the liquid yet, there will be a given portion of molecules existing as vapor that will be constant. That's what we call the vapor pressure, or the pressure of vapor at a given temperature. We are not boiling the liquid yet. That will be at a higher temperature. And yet, even though we have not boiled the liquid, there's always a fraction, a tiny fraction or a larger fraction, depending on the liquid and the temperature, that those molecules existing as vapor. So you may be wondering some questions, such as this one. What will happen to a liquid if we leave the bottle opened? Well, if you leave it for long enough, the molecules escaping will never come back. This means that the equilibrium will never be reached. There will never be enough molecules coming back to liquid, so you'll have a complete evaporization, even though we are below the boiling point. Even though we are below the boiling point, if you leave your bottle open, so you can try that, you can leave overnight a cup of water on the counter and come back maybe the morning after and see how much water is left. There will be some that will have evaporized and never came back. So how is that related to the specific kind of liquid? So how can you relate strength of intermolecular forces, enthalpy of vaporization, and vapor pressure? Well, you can imagine that the stronger the intermolecular forces, you already know that the higher the enthalpy of vaporization, that is the higher the energy that it takes to vaporize that compound, and therefore at that given temperature the lower will be the fraction of molecules in gas form. That is, the lower will be the vapor pressure. This is a very important relationship that should make sense, because as the molecules interact with each other more strongly in the liquid, they'll be less likely to be in gas form. Okay, so their vapor pressure will be lower.